Hello, I am Professor S. Shankaran in the Department of Metallurgical and Materials Engineering.
We will just summarize some of the quantities which we have already learned. So we started with the stress-based approach of fatigue, which has got an important implications in rotating machinery subjected to alternating stress, pressure vessels subjected to periodic loading and unloading, aircraft fuselage subjected to pressurization and depressurization during takeoff and landing of respectively. However, most of the engineering components generally undergo certain degree of structural constraint. So this is very different from the above 3 points. And localized plastic flow, particularly at locations of stress concentrations. So wherever the components, they undergo certain degree of structural constraint and localized plastic flow, we need to go for the other way of approach. That is, stress-based approach takes care of these kind of loading. And in these constrained situations, it is more appropriate to consider the life of the fatigue component under the strain controlled condition, which represent the constrained loading situation. So here, why I'm trying to kind of justify why we look at stress-based approach as well as strain-based approach. Though we have seen both of them already, now I'm just kind of summarizing and then bringing into a kind of combined discussion. So the strain-based approach to total life is generally analyzed by a Coffin-Mansion. This is called Coffin-Mansion plot. We normally refer in fatigue community. Coffin and Mansion, working independently on thermal fatigue problems, proposed a characterization of fatigue life based on the plastic strain amplitude. They noted that log-log plot of plastic strain amplitude and 2NF to failure, a linear relationship resulted for a metallic materials. Very, very important point. People work, if you want to characterize the plastic strain controlled fatigue, this is the first plot everybody will look at. Okay, so which is delta epsilon P by 2. This is a plastic strain amplitude, which is equal to epsilon F prime into 2n to the power C, where delta epsilon P by 2 is a plastic strain amplitude. Epsilon F prime is a fatigue ductility coefficient defined by the strain intercept at 2n is equal to 1. Epsilon F prime is approximately equal to the true fracture strain, epsilon F for many metals. 2n is number of strain reversals to failure. One cycle is 2 reversals. And C is equal to fatigue ductility exponent, which varies between minus 0.5 to minus 0.7 for many metals. So this is a very important relation as per the strain-based approach to total life. And then we know that stress-based relation, which is given by the Baskin equation, which we have seen earlier, which reads like this: delta epsilon E by 2 into T is equal to sigma F prime into 2n into 2 power B. So this sigma A is alternating stress amplitude. This is as elastic strain amplitude, E Young's modulus. Sigma F is fatigue strength exponent. And so this is similar to sigma F, and B is the fatigue strength exponent. So now we have these two equations. We will see if we put together how does it look like. So this is what is shown here. An equation valid for entire range of fatigue lives can be obtained by this kind of an equation. So one is strain based, another is stress based. So delta epsilon by 2 is equal to delta epsilon E by 2 plus delta epsilon P by 2. So if you can just substitute this from Baskin and Coffin-Mansion plot, you get this equation, and then you have a common expression for this NF, which is 2NF total, N total. And this plot very nicely illustrates the Coffin-Mansion plot versus Baskin plot. This is a combined curve. You can see that. Okay. At short life, that is when 2NF is less than 2n of t, plastic strain amplitude is more dominant than the elastic strain amplitude, and the total fatigue life of the material is controlled by ductility. See, this is how you should appreciate how to read these equations, right? At long fatigue life, that is when 2nf is much greater than 2nf total, the elastic strain amplitude is more significant than the plastic strain amplitude, and the fatigue life is dictated by the fracture strength. Okay, so which fatigue test or what type of fatigue study will give what type of material behavior, something like that. Okay, optimizing the overall fatigue properties that inevitably requires a judicious balance between strength and fatigue. So this is a well-known challenge. Even today, people work on different modern materials. Still, this is the strength versus ductility is a huge challenge, right? Okay, now we will now look at the little bit on fatigue crack growth mechanisms. Though we have seen this already in the fracture mechanics chapter elaborately, I just want to touch upon some of these small features or important points which we have missed in that chapter. Okay, so this is you know now very well about this fatigue crack growth, which is divided into three regions: region A, region B, region C. And this is described, I mean, region B is described by the Paris equation. Okay, and region 1 is the important parameter, design parameters, delta K threshold is we have discussed, and then region 3, the material can reach the K1C. Okay, so that is how it is. So in fact, this particular equation, Paris law, is a link between fatigue and fracture mechanics, and very important design parameters this equations gives. Okay, though it is an empirical relation, but it is very important relation. And some salient features concerned to near threshold fatigue crack growths I want to just mention. The stress intensity factor range approaches the fatigue crack growth threshold delta K. An operational definition for delta K naught or delta K threshold, the same here, is commonly used in terms of maximum crack growth rate, typically 10 to the power minus 8 mm, based on the accuracy of the crack monitoring system and the number of elapsed cycles. Structural engineers are often faced with the task of designing components which can withstand very high frequency, low amplitude loads over fatigue lifetimes as high as 10 to the power minus 10 to 10 to the power minus 12 load reversals. For example, a high-speed turbine rotor operating at 3000 revolutions per minute may be subjected to 10 to the power 10 stress cycles over a typical lifespan of 20 years. Suppose if you take this as an example, if the fatigue crack growth were to occur in this rotor at seemingly insignificant rate of 3 into 10 to the power minus 9 mm per cycle, that is 1/100th of an atomic spacing per cycle, this would still represent a total crack advance of 30 mm during the life of the rotor, which is sufficient to cause a catastrophic failure. So now this clearly demonstrates why we need to worry about the threshold, fatigue threshold, delta K values. That is one idea. And if you look at the threshold values for typical alloys, structural alloys, this is delta K versus R. This is a stress ratio. You can see that typical range of delta K values as a function of a load ratio for variety of iron, nickel, copper, titanium, aluminum alloys. And note that the threshold values for different alloys exhibit significantly less variation at high R values than at low R values. So that is quite obvious. At low R values, the the delta H threshold range is quite high. As the R increases, that means it goes higher mean stress. We have seen in the beginning of the lecture, it all comes down. The ranges comes down. This is something you have to know. And now we get into this crack growth mechanisms. What you are seeing is a very nice picture showing the fatigue striations on an etched failure surface in 2024 T3 aluminum alloy. This is also a book cover of this book by Professor Suresh. So very nice image. So striations are characteristic of fatigue crack growth, which this particular striations get generated in the material in the crack growth regime of 2. This is what we have seen in the last chapter also. Just to give you one more model. There are several models reported in the literature, but one model I just want to discuss, which I did not discuss in the fracture mechanics chapter. So this is a very nice schematic which is describing this. An idealization of plastic blunting and resharpening, which leads to stage 2 crack growth in a fully reversed fatigue. So this is a model for the striation formation in the stage 2 of the crack growth curve. So what is shown here is what is A. Suppose you consider the crack like this, and which is at a 0 load, okay. And if the small tensile load is increasing, then this crack becomes like this. It opens up, and sorry, here this is not the. Sorry about this. I'm supposed to show this. This is the small tensile load, and then the moment it reaches the peak tensile load, and what you have to observe is it is a crack blunting. So this is crack blunting occurs, and then what happens in a D, onset of load reversal. So it becomes that means the crack opening displacement comes down, and what happens to this blunt surface is again becoming a 2 sharp edges, okay, because of the reversal loading. And this is peak tensile, and this is a peak compression. So peak compression, what happens is very interesting to note. So you compare this crack length and this crack length. The crack length is extended by this mechanism. By compressing further, this sharp edges become further sharper and becomes another new edge, and it's ready to go back to this model again. Okay. So again, small tensile load in the subsequent tensile cycle lead to this. So this becomes this, but you can see the length has been increased compared to this one. So arrows shows the disk slip direction, and this is proposed by Laird. And this one particular mechanism is a model mechanism for the striation formation, because striation is the characteristic of fatigue loading alone. That's why I just want to bring this idea so for the completion. And one more important aspect is as I just mentioned, this Paris law connects the fracture mechanics and fatigue, and with this we will be able to calculate the life of the fatigue specimen from this relation. I want to show this equation, how we can understand this. So this is a Paris equation, and you can see that you can rewrite this equation like this, and we know that the crack length is obtained by the stress intensity factor equation, which is AF is equal to 1 by pi into Kc divided by sigma max into alpha to the power 2. So alpha is the material parameter, and if you integrate this expression, and then we can integrate from the initial crack length. I mean, this is the initial loading to final cycle, initial cycle to final cycle dn, which is equal to integration of initial crack length to finite crack length into dA by A into alpha to the power P and sigma R to the power P and pi A to the power P by 2. So the what is shown here is sigma R is the stress reversal, complete reversal. So it is delta sigma is replaced like sigma R, and in some books it is P is the exponent is written as M, but here it is in this reference it is given as a P. So we can just go ahead with that. So after integration, after rearrangement, then you have to finally reach this integral value, integral AI, limits to AI to AF, dA by A to the power P by 2. So if you perform this integral for the value of not equal to 2, the P value, normally it is 3 to 4 for most of the metals, but in this particular case it is derived for if P is not equal to 2, then it has to go in this way. And if you substitute this, carry out the integration and then substitute the limits, then you get this final expression. And what you have to remember is this is not, taking care of the crack length, right? The crack length versus the alpha dependence on the crack length is ignored here. But if you consider alpha as a function of crack length, then this equation has to be used for calculating the NF. Okay. So we will solve some numericals in the tutorials, then you will appreciate this. So what I want you to know is through this Paris equation, we will be able to calculate the life of the component subjected to fatigue loading. So this is one demonstration about that. The other point I want to just summarize is mechanisms of crack closures. We have already seen this in the fracture mechanics. Just to recall, and whatever is we have already discussed. One of the important crack closure mechanism is the plastic zone size developing ahead of the crack tip. So we have seen this is a plasticity induced crack closure. See, as you move ahead, the plastic zone size bigger and bigger, then the crack get resistance or get closed sometimes. Then oxide film induced crack closure, roughness induced crack closure, especially in a mode 2 kind of situation, and fluid induced crack closure is there, and transformation induced crack closure also we have seen. That is, in fact, we will just see the one classical example for this transformation induced plasticity. We will see as a case study, and crack deflection mechanisms by obstacles or second phase particles, and crack bridging by fibers. This is for composites materials, and crack bridging by particles. We said that wedging action in the fracture mechanics chapter, similar to that, and crack shielding by micro cracks. This also we will see now in another 1 or 2 slides. There is a case study you will see, and crack shielding by dislocation. This is also possible. So this is several mechanisms which supports the crack closure behavior. Some of the basic features are: closure is more dominant at lower delta K and lower R values because of the smaller minimum COD of the fatigue cycle. And there is a characteristic size scale associated with each closure process. That is, if the plasticity induced process is considered, then height of the residual plastic crack weight stretch, that is to be very important parameter for the crack closure. If it is an oxide induced crack crack closure process, then the thickness of the fracture surface oxide layer, that will play a major role for the crack closure process. And if it is a roughness induced process, then height of the fracture surface asperities. Okay. And if it is a transformation induced process, then the height of the transformation zone, which is going to determine the crack closure effectiveness. When the size of this characteristic closure dimension becomes comparable to COD, crack opening displacement, premature crack face contact has mod, which is an effect of crack growth, fatigue crack growth rate. Okay. So any of these dimensions has to be much smaller compared to COD, then the premature fracture will not take place. Otherwise, this will be more effective. It will show more effect on the fatigue crack growth rate. Beyond certain crack length, closure is normally crack length independent. Effect of stress state on the extent of crack closure. The unique conclusion can be reached. Plasticity induced crack closure is more dominant in the plane stress than the plane strain under the cyclic tension. However, the reverse situation occurs in the cyclic compression. So this is one important effect of state of stress on the crack closure. So now I just want to briefly discuss the fatigue of brittle solids, very highly brittle solids. Most of the aspects we have discussed are confined to metals and alloys. And let us see some of the interesting ideas about brittle solids. In brittle solids, we consider the kinematic irreversibility. What is that? The processes which impart kinematic irreversibility to microscopic deformation during the fatigue of brittle solids include a frictional sliding of mating faces of microcracks. So we are now going to talk about microcracks. In fact, even Griffith considered microcracks as the basic units in the glass. Right? So similarly, same approach. Here we are talking about frictional sliding of mating faces of microcracks that are nucleated at grain boundaries at interface regions and interfaces between matrix and the reinforcement. Wedging of the mating surfaces of microscopic and macroscopic flaws by debris particles, which are formed as a consequence of repeated contact between the crack face under the tensile and compressive cyclic stresses. Okay. And microcracking due to release of thermal residual stresses at grain boundaries and interfaces and promotes permanent transformation strain. The inelastic strain arising from the shear or dilatational transformation such as mechanical twins, martensitic lamella or crasis. The viscous flow of glassy phases that are introduced during processing are associated interfacial cavitation in ceramics and ceramic composites during the high temperature fatigue. So all these aspects, the very important aspects, will contribute to the kinematic irreversibility. Okay, so this is how you should connect these events. Okay, all these events we know. We are not talking anything new here. Most of these things we are discussed in the form of crack closure. But in a brittle solid, all these small microstructural events contributes to the kinematic irreversibility, how it affects the fatigue behavior. That is how we should discuss now. Before we discuss the mechanisms, we will also define what is the degree of brittleness. We can classify highly brittle, semi-brittle and non-brittle materials. And in a highly brittle material, the main factors are bond rupture. Example is diamond structure, zinc blende structure, silicates, alumina, mica, boron, tungsten, carbides and nitrates. In semi-brittle materials, the main factors which is going to characterize the failure is bond rupture, dislocation, mobility. For example, sodium chloride structure, other ionic crystals, HCP metals, most BCC metals, and glassy polymers. They are coming under semi-brittle classification, and a non-brittle is dislocation mobility, FCC metals, non-glassy polymers, silver halides, some BCC metals. So the degree of brittleness is measured by these parameters and factors, and these are all the material examples for that. One example is shown, a practograph is shown as an example, a zone of grain boundary microcracks in the alumina subjected to compressive stresses. So you see that all the boundaries are highly cracked, completely cracked microcracks in alumina. And this is in TEM foil taken very close to the tensile fracture surface in zirconia toughened alumina. So you can see that all microcracks are marked with the features in the grain boundaries. So how do we understand the stress strain curve for a microcracking material? Very interesting idea.